Hi, I'm Pau Rodriguez and I'm going to present Consistency CAM, our new work to improve weakly supervised semantic segmentation. This is joint work with Sai Rajeswar, Isam Laraji, David Vázquez, and Aaron Curville. We focus on the problem of semantic segmentation, which consists in labeling each of the pixels of an image. However, labeling pixels requires a lot of effort compared to other levels of supervision, such as image level labels or point level labels. This motivates the field of weakly supervised semantic segmentation, which focuses on leveraging weaker forms of supervision to achieve pixel level segmentation models. Thus, we only consider image level labels in this work. Typical pipelines for weakly supervised semantic segmentation are trained in two stages. In the first stage, we train an image classification network with global average pooling or GAP. Once trained, we can remove the average pooling to obtain 2D class activation maps that resemble segmentation masks. In the second stage, we can train a segmentation network using some CAMs as pixel level supervision. A problem with using CAMs is that they are noisy compared to the real labels. That's why many methods in the literature introduce an intermediate stage that refines CAMs with some regularization loss. A recent example that achieves good CAM refinement is Puzzle CAM. In this work, the authors split the image into multiple tiles and introduce a new loss to ensure that the CAMs for the whole image matches the CAMs obtained after stitching the CAMs for each of the individual tiles. In our work, we identify three key improvements to Puzzle CAM. First, we argue that pre-training the backbone for single label prediction might have a negative effect in segmentation performance, since image segmentation datasets usually have more than one class per image. Thus, we train the backbone with multi-label iterated learning, or MILE, which learns a multi-label representation from singly labeled images. Second, GAP enforces the network to overrepresent the labeled objects in the feature maps. Thus, we replace it by a differentiable noisy OR operation, which marks a class as present in an image in a way that is independent to the number of pixels that belong to that class. Finally, we observe that PuzzleCam uses fixed tile sizes, and that the puzzle operation could be complemented with any other transformation. So we propose a more general set of transformations. The final model, which we call Consistency CAM, is summarized in these two pictures. In the left picture, you can see the noisy OR operation and the multi-label iterated learning framework that uses the teacher-student framework. The noisy OR operation is different from GAP in that it does not perform an average of the class activations in the feature map. With noisy OR, a class will be active with high probability even if only one pixel is activated for that class. To ensure the backbone is able to predict multiple classes per image, we use multi-label iterated learning, or MILE. The procedure to train a model with MILE is as follows. First, we train a teacher network with single labeled images for a few iterations. Then, a student network is spawned from the teacher network. The teacher network starts producing labels for images that contain multiple objects. After training for a few iterations, the student becomes the teacher. We repeat this process until convergence. After the backbone is trained, the resulting CAMs are noisy. To improve them, we use a consistency reconstruction loss to ensure that the CAMs are robust to a different set of augmentations as well as the puzzle operation with different tile sizes. Now I'm going to show some results we're applying these improvements to PuzzleCam. Here we show some results on Pascal and Coco. As you can see, our method improves PuzzleCam by several points. In the left panel, we also see that training the backbone with multilabel learning is beneficial. Here we show some qualitative results. As you can see in the right panel, our method results in more accurate segmentation masks. To conclude, we propose 3 improvements for weakly supervised semantic segmentation based on CAM and concretely on PuzzleCam. First, we pre-train the backbone for multilabel classification. Second, we change the gap operation by a noisy OR operation. Third, we propose a more general set of augmentations for CAM refinement. Finally, these 3 improvements result in better performance on Coco and Pascal. Thanks for your attention and see you at the poster.